In the previous videos, we covered Newton's laws of motion, the different types of forces that you are likely to encounter in your study of basic physics, and we also covered the first condition of equilibrium. Putting them all together, let's now have net force analysis or simply force analysis. When doing force analysis, follow these steps. Draw the system if no diagram or drawing is provided by the problem. If there's already a figure provided by the problem, you can go on to the next step. But if no drawing or figure is provided, then that's the first thing that you should do. Read the problem and then draw the figure or diagram as described by the problem. Next step, using the drawing of the system, identify the forces that are present in the system, which stands to reason. How can you analyze the forces? How can you do force analysis if you don't know what forces there are that are present in the system? So identify the forces present in the system. Then using the forces that you have identified, draw the free body diagram, FBD. There may be more than one depending on the situation. Typically, one object, one free body diagram. Basically, a free body diagram is a vector diagram. Draw the forces and other relevant vectors that are present in the system. And then finally, analyze the free body diagrams using either F net is equal to 0 for equilibrium system or F net is equal to MA for accelerating system. And don't forget to use your component method when adding forces together when doing net force. You'll recall again, F net is equal to summation of all the forces that are acting on the object. So that's basically vector addition. So don't forget to use your component method when doing force analysis. So let's have a couple of examples and then we'll apply the steps that we have just covered, the steps for force analysis that we have just discussed. First, we have sample problem number 1. You have a string tied to box A and passed over a frictionless pulley. Box B is attached to the other end of the string. Box A has a mass of 2.5 kilograms. If the coefficient of static friction between box A and the tabletop is 0.75, what is the maximum mass that box B can have and still have the system in equilibrium? The problem provides a figure. You have box A, box B, tied with a string. The string is passed over a frictionless pulley. There is static friction between box A and the horizontal tabletop, which means static friction, which means the system is in static case. The problem tells us equilibrium. Therefore, the system is in static equilibrium. Mass of box A is 2.5 kilograms. Knowing the mass, we know the weight because we know the equation for weight to be simply mg. Magnitude of weight A is equal to mag, where g is magnitude of acceleration due to gravity. In this case, it is equal to 9.8 meters per second squared. We are able to calculate the weight magnitude of box A, 24.5 newtons. The problem also gives us the coefficient of static friction between box A and the tabletop. Mu S is equal to 0.75. Since the problem has already provided a drawing of the system, you don't have to draw the system anymore. You can go on to the next step. Identify the forces present in the system. We've already identified one. Since A has mass, it has weight A vertically downwards. B also has mass. That's what we are looking for. Maximum mass of box A, box B rather. So B has mass, it has weight B vertically downwards. Because of weight B, the string is being stretched. The string will react by applying tension. So there is tension in the string. Note that the string is passed over a frictionless pulley. A frictionless pulley will have no effect on the value of the tension inside the string. Its effect is on the direction of the tension. It redirects the string from horizontal to vertical orientation. The same goes for the tension. The tension in the string will be horizontal in this location and vertical in this location. So the string will apply tension T on box A and will apply tension T on box B. And the tension for both boxes, the tension experienced by both boxes are equal because there's only one string and the pulley is frictionless. Because of weight A, box A is pressing into the table. The surface will react by producing normal force N. The surface is horizontal, therefore the normal force is vertical. And because of tension T, box A is being pulled to the right. Static friction will arise to oppose that impending motion. Static friction will be heading to the left. In identifying the forces present in the system, we have drawn the free body diagram. We have two objects, therefore we have two free body diagrams, one for box A and one for box B. Starting with box A, we have free body diagram 1. The system is in equilibrium. So in analyzing the free body diagram, we set the net force to 0. So F net is equal to 0. F net is summation of all the forces acting on box A. So we have normal force, tension, weight A, and friction. So summation of all those forces is equal to 0. And because these forces are vector quantities, we use component method to analyze the summation. So we have X component and we have Y component. Y component, X component rather of F net, you have F net X. X component of 0 is 0. Weight A and normal force are both vertical. They don't have X components. Friction is horizontal, negative direction, so minus F sub S. Tension is horizontal, positive direction, so plus T. From X component, we see that tension magnitude is just equal to static friction magnitude. Going now to the Y component, F net, Y component, you have F net Y. Y component of 0 is 0. Weight A is vertical, negative direction, so minus weight A. Normal force N is vertical, positive direction, so plus N. And as we have mentioned, static friction and tension are both horizontal. They don't have Y component. So from y component, we see that the normal force is just equal to weight A. And we know weight A magnitude to be 24.5 newtons. Going now to the next free body diagram. Free body diagram on box B, you have FBD2. So we do the same thing. F net is equal to 0. The system is in equilibrium, in particular, static equilibrium. On box B, the only forces are weight and tension. So summation of the forces acting on box B, you have weight B plus tension T. So F net is equal to 0, equilibrium, summation of the forces, weight B plus tension T. Weight B is negative direction, tension T is positive direction. Both are vertical, so no x component. So no x component. We go directly to y component. Y component of F net is F net y. Y component of 0 is 0. Weight B is vertical, negative direction, so minus weight B. Tension T is vertical, positive direction, so plus T. From y component, we see that tension magnitude is just equal to weight magnitude. Weight B magnitude is just mBg. We are looking for maximum value of mB, so we isolate mB and set it to maximum value. G is constant at 9.8 meters per second squared, meaning if we want to get maximum MB, we have to set tension T to maximum value. And you will recall that tension T is just equal to static friction between box A and the tabletop. Static friction ranges from 0 to a maximum value. So if we set static friction to maximum value, mu Sn, tension T will also be maximum value. And maximum value of static friction, Fs max, is mu Sn, where N we know to be equal to weight A. So T max is equal to mu S weight A, which means MB max is just equal to mu S weight A divided by G. Plotting in the values, we are able to get the maximum value of MB, 1.875 kilograms. Next, we have sample problem 2. A string is tied to box A and passed over a frictionless pulley. Box B is attached to the other end of the string. Box A has a mass of 2.5 kilograms, whereas box B has a mass of 3 kilograms. If the coefficient of kinetic friction between box A and the tabletop is 0.6, determine the acceleration of the system. And once again, the problem provides a figure, a drawing of the system, so you don't have to draw the system. You can move on to the next step, identifying the forces present in the system. You have mass A. Mass of box A is given 2.5 kilograms. And once again, knowing the mass, you are able to determine the weight magnitude of the object. Weight is just equal to mg. So knowing ma to be equal to 2.5 kilograms, we can easily calculate weight A magnitude to be 24.5 newtons. And we do the same thing for box B, knowing the mass of box B to be mb equal to 3 kilograms. We are able to calculate the weight magnitude of box B 29.4 newtons. And the problem also provides coefficient of kinetic friction. Mu k is equal to 0.6. We know weight A vertically downwards. We know weight B vertically downwards. Because of weight B, the string is being stretched. The string will react by applying tension. So you have tension T applied on box A and tension T applied on box B. Once again, the pulley is frictionless. So it only redirects the direction of the orientation of the string. Thus, tension on box A is horizontal, whereas tension on box B is vertical. Weight A is pressing into the table surface. Therefore, the table surface will react by producing normal force N. Because of tension T, box A is being pulled to the right. Kinetic friction will oppose this motion. Kinetic friction will be heading in the opposite direction. So you have F sub K. We know kinetic friction because the problem tells us there is kinetic friction coefficient between box A and the tabletop. Likewise, the problem tells us that we are looking for the acceleration of the system. So that means the system is moving. For existing sliding motion, kinetic friction will arise to oppose that motion. Now, this problem you will notice is similar to the problem in the first example that we have just discussed, but this time there is acceleration of the system. So the system is an accelerating system. So we also have to identify the acceleration of the system. Box B is being pulled downwards by its weight. Therefore, in all likelihood, box B will move downward. That means the acceleration of box B is downward. Since box A is tied to B, if B moves downward, box A must move to the right. The acceleration of A must be to the right as well. So we have acceleration A to the right and then downwards. And since the system is moving as one, the magnitude of these two acceleration are the same. The only difference is their direction. Now that we have identified the forces, we have also drawn the free body diagram in identifying the forces. Let's now analyze these free body diagrams. This time we have an accelerating system, so we set the F net to MA. So starting with the free body diagram on box A, free body diagram 1, we set F net to MA. So you have F net is equal to MAA. F net is summation of the forces acting on the object. So you have weight A plus normal force N plus kinetic friction F sub K plus tension T. And once again, we use component method to do our analysis. So X component of F net is F net X. X component of acceleration for box A, acceleration is horizontal, positive direction. Weight A and normal force are vertical, no X component. Friction, kinetic friction F sub K is horizontal, negative direction, so minus F sub K. Tension T is horizontal, positive direction, so plus T. Isolating tension T, we have T is equal to MAA plus F sub K. F sub K is just equal to mu K N. Going now to the Y component, F net Y is equal to 0. Acceleration of A rather is horizontal, so no y component. So MAA is 0 on the y component. Weight is downward, so minus weight A. Normal force is vertically upward, so plus N. Kinetic friction and tension are horizontal. No y component. From the y component, we get that the magnitude of normal force is just equal to magnitude of weight A. Going now to box B, free body diagram. Free body diagram 2, we do the same thing. Box A is accelerating, so F net is equal to MA, MBA, and F net is summation of the forces acting on box B, so you have weight B plus tension T. If you look at the diagram, all the vectors are vertical, no x component. So we go directly to the y component. So F net, y component of F net y component of acceleration. Acceleration is heading downward, so negative direction, so minus mba. Weight is downward, tension is upward, so weight is negative direction, tension is positive direction, so minus weight B plus tension T. Isolating tension T, we get to be equal to weight B minus MBA. We have two equations for tension. The equation that we got for free body diagram 1 and the equation that we got from free body diagram 2. Equating the two equations, we have MAA plus mu Kn is equal to weight B minus MBA. MAA is equal to mu K weight A. Normal force is just equal to weight A. Is equal to weight B minus MBA. The only unknown is A, the acceleration A. So isolating A and plotting in the values, we get the acceleration of the system to be equal to 2.673 meters per second. And that's it for now. In the next video, we'll cover more examples. So thank you for watching.